Hello, in this video we're going to talk about approximating functions by polynomials. So imagine you want to evaluate, say, sine of x for some value of x. Evaluating that would be complicated because it's not a function that there's like a easy algorithm for finding its sine. So we have algorithms for adding, multiplying, dividing, raising to powers, but evaluating something like sine of x, since it's not a polynomial, it cannot be evaluated by simple addition, multiplication, and division, is not going to be easy. So what we want to do is we want to build some tools to be able to approximate functions using polynomials, since the simplest functions are polynomials, which we can easily evaluate. So, but first we want to understand what it means for two functions to be close to each other. So here is the definition that tells us gives us some understanding of closeness of two functions. So if you have two functions, they could intersect at a point, and that clearly would be they would be close to each other at that point. However, if they cross like this, then they're going to be only close at that specific point, and then immediately they're going to go in different directions, which means they're going to get far from each other. If, however, you choose two functions that not only they touch each other, but they also go along the same direction. In other words, the values at that point are the same and the directions are the same, meaning that the tangent lines are the same. Then those two functions are even closer. So in this example, f of x naught and g of x naught are the same. These are two functions, f and g. In this example, not only the values are the same, but their derivatives are also the same. So this brings me to definition 8.1. Let I be a neighborhood of a real number x naught. Two functions f and g are said to have contact of order at least 0 if they intersect. If f of x naught is equal to g of x naught, we say f and g have contact of order at least n if not only f of x naught and g of x naught are the same, but f prime of x naught and g prime of x naught are the same, and all the way to fn of x naught and gn of x naught. So if all of these are the same, then we say f and g have contact of order at least n. Why do we call it at least n? Because it could also be n plus 1. So if the next one is not 0, then we say they have contact of order exactly n. Okay, so here is an example. So we're going to go over this one, and then we will do a very important theorem. Prove that the functions e to the x and 1 plus x squared over 2, which is a polynomial, these two have contact of order 2 at 0. So what I need to do is to evaluate f prime of x, f double prime of x, and show that at 0 these two are the same as g prime of x and g double prime of x. And then the next one, they are not the same. So f prime of x and f double prime of x and f triple prime of x, they are all e to the power of x. So that means f of 0, f prime of 0, f double prime of 0, and f triple prime of 0, they are all equal to 1. If you look at g of x, which is 1 plus x squared over 2, when you differentiate, you get 1 plus x. When you do the second derivative, you get 1, and when you do the third derivative, you get 0. So that means f of 0 and g of 0 are the same. F prime of 0 and g prime of 0 are the same. F double prime of 0 and g double prime of 0 are the same. But the third derivatives are not the same. And that means f and g have contact of order 2 at x equals 0, which is what we wanted to show. So the derivatives up to the second derivatives are the same, but the third derivatives are different. Okay, so now the question becomes, if I have a function, then can I find a polynomial that has contact of large order with that function? And the answer is in fact yes. So let's look at this theorem, and then we will go over the proof of this theorem. So let I be a neighborhood of x0 and n be a non-negative integer. Suppose f from I to r has n derivatives. Then there is a unique polynomial Pn of x of degree at most n that has contact of order at least n with f. So for any function that you take, there's a polynomial of degree at most n, so the degree is at most n, and the contact is at least n. And in fact, we have a formula for that polynomial. It is f of x0 plus f prime of x0 times x minus x0, f double prime of x0 over 2 factorial x minus x0 squared, all the way to fn of x0 over n factorial x minus x0 to the power of n. So we're going to prove this one. The first thing we need to notice is that if you have a polynomial of degree n or degree at most n, then you can write it down. So let me write it down. So any polynomial of degree at most n has the form some constant plus constant x. That's like basically what the definition of a polynomial is, all the way to a n x to the power of n. However, if you replace each of these x's, substitute x by x minus x0 plus x0 and use this. So when you have x to the power of k, replace it by x minus x0 plus x0 and then raise it to the power of k. So this would give you the sum k choose j equals 0 to n x minus x0 to the power of j x0 to the power of k minus j. So in other words, therefore every polynomial of degree at most n has this form, has the form c0 plus c1 x minus x0 plus all the way to cn x minus x0 to the power of n. When you substitute x to the power of k by this quantity and then expand it, you get a bunch of x minus x0 to two different powers, starting from constant all the way to x minus x0 to the power of n, which means every polynomial of degree at most n would have this form. Okay, so now let's assume that this polynomial has contact of order at least n with f. So Pn of x equals c0 plus c1 x minus x0 all the way to cn x minus x0 to the power of n has contact of order at least n with f at x0 if and only if, by definition, the definition is k of x0 is equal to Pn k of x0 for k equals 0 to n. So this is if and only if, because that's just the definition. So let's evaluate Pn, derivatives of Pn at x0. So let's evaluate Pn prime of x. Pn prime of x. Pn prime of x would be c0 becomes c0, becomes 0. c1 times x minus x0 becomes c1. c2 becomes 2c2 x minus x0. This third one becomes 3c3 x minus x naught squared. The next one would be 4, and so on. c4 x minus x naught cubed. And finally, the last one becomes n cn x minus x naught to the power of n minus 1. So that means if I plug in x naught, I would get c1 because everything disappears. If I take the second derivative of the previous one, I would get c1 disappears. I would get 2c2 plus 3 times 2c3 x minus x naught plus 4 times 3c4 x minus x naught squared all the way to n times n minus 1 cn x minus x naught to the power of n minus 2. And then if you plug in x naught, pn double prime of x naught becomes 2c2. If you differentiate again, pn triple prime of x becomes 2c2 is going to become 0. It becomes 3 times 2c3 plus 4 times 3 times 2, and you start seeing the pattern. c4 x minus x naught all the way to n times n minus 1 times n minus 2 x minus x naught to the power of n minus 3. So maybe I will bring that down. And if I plug in x naught in there, pn triple prime of x naught becomes 3 times 2c3. And you can see the pattern here. So that means pnk of x naught is equal to k factorial c times k. So in order for pn to have a contact of order at least n, this quantity must be the same as the nth derivative of f. So this has contact of order at least n with f of x at x naught if and only if pnk of x naught is equal to fk of x naught. And this is clearly the same as k factorial ck equals fk of x naught, which is the same as saying ck is equal to fk of x naught over k factorial, which is to say pn of x is equal to the sum fk of x naught over k factorial times x minus x naught to the power of k. K equals 0 to n. So what we just showed is that there is exactly one polynomial of degree at most n that has contact of order at least n with a given function. Okay, so now let's look at some examples. And this polynomial Pn of x is called the nth Taylor polynomial of f. Note that the degree of this polynomial may not be exactly n. It could be less than n, but it would not be more than n. So let's now look at some examples. So we will find the nth Taylor polynomial of each of the following functions at 0. So our x naught is 0. So we are going to have to find the derivatives of each of these. So if you take the nth derivative of the first one, that's just e to the x. So that means fn of 0, or let me use a different variable. So that's just 1. So that means Pn of x becomes the sum k equals 0 to n 1 over k factorial times x to the power of k. So this is the nth Taylor polynomial. Next one is 1 over 1 minus x. And we can prove this one by induction. So this is very easy to prove because the derivative of e to the x is itself. Let me write it down here. If you look at the next one, so sometimes it becomes less clear, so you'll have to write down a proof by induction. This one was pretty obvious. If you look at the next one, you'll find the derivatives. You can do the work maybe on the right, and then we'll write it down. So the first derivative is going to be minus, this is 1 minus x to the power of -1. So by the chain rule, we get 1 minus x to the power of -2 times the derivative of inside. So that's 1 minus x to the power of -2. If you take the second derivative, it becomes -2 1 minus x to the power of -3 times the derivative of inside. So that's 2 1 minus x to the power of -3. If you take this third derivative, you get 2 times -3 1 minus x to the power of -4 times -1. So that is 3 factorial 1 minus x to the power of -4. So you can kind of see the pattern here. So we are going to prove this one by induction. By induction, we will prove that gk of x is equal to k factorial times 1 minus x to the power of -k minus 1. For k equals 0, g of x is 1 minus x to the power of -1, and 0 factorial 1 minus x to the power of -0 minus 1 is also 1 minus x to the power of -1. So that means the basis step is proved. Okay, so that's for k equals 1. Suppose gk of x is equal to k factorial 1 minus x to the power of -k minus 1 for some k. By the chain rule, gk plus 1 of x becomes k factorial -k minus 1 1 minus x to the power of -k minus 2 times -1, which is k factorial times k plus 1 1 minus x to the power of -k minus 2, which is k plus 1 factorial 1 minus x to the power of -k minus 2. Okay, and this is exactly what we wanted to prove. This is k plus 1 factorial 1 minus x to the power of -k plus 1 minus 1, which matches the claim that we wanted to prove. Therefore, gk of x is in fact k factorial 1 minus x to the power of -k for every k, for every integer k, or for every k greater than or equal to 0. Okay, so this tells us that if we look at the nth Taylor polynomial, we get the sum k equals 0 to n. We can plug in gk of 0 here. So that would be k factorial 1 minus 0 to the power of -k over k factorial times x to the power of k. So this would become the sum k equals 0 to n x to the power of k. So that's the nth Taylor polynomial for 1 over 1 minus x. Okay. So the last one is natural log of 1 plus x. So this one is h of x is natural log of 1 plus x. So we're going to do the same thing. We're going to find a bunch of derivatives and then see what the pattern is, and then we prove that by induction. So h prime of x is 1 over 1 plus x, which we can write as 1 plus x to the power of -1. H double prime becomes -1 plus x to the power of -2. H triple prime becomes, you put the -2 in front, 1 plus x to the power of -3. h4 of x becomes negative 6, which you kind of see it's 3 factorial. 1 plus x to the power of negative 4. h5 of x becomes plus 4 factorial. 1 plus x to the power of negative 5. If you don't see the pattern, write down a few more. But by that point, it's fairly clear. So we claim that hk of x, for k equals 0, the pattern is different. This one is natural log, but these are powers of 1 plus x. So I'm going to start from k equals 1. That is, first the coefficient is k factorial. The first one is 1 factorial, although the second one is also 1 factorial. The third one here is 2 factorial. So it's a little bit different from k factorial. The fourth one is 3 factorial. So that would have to be k minus 1 factorial. The signs alternate. For 1, we get plus sign. For 2, we get negative sign. For 3, we get positive sign. For 4, we get negative sign. So it's a negative sign, but it's negative 1 to the power of k plus 1. And then, of course, I have the k minus 1 factorial. And then we have the exponent of 1 plus x, which is negative 1 for 1, negative 2 for 2, negative 3 for 3. So it's negative k. And this is for all k, but starting from 1. So first h basis step, pretty easy to prove. H prime of x is 1 over 1 plus x, which is 1 plus x to the power of negative 1. And negative 1 to the power of 1 plus 1 times 1 minus 1 factorial, 1 plus x to the power of negative 1 is the same thing, because that's positive, positive 1, 1, that's just 1 plus x to the power of negative 1. Now inductive step. Suppose, did I mention I'm using contradiction? I didn't. So I'm going to actually mention, because I would like to always mention what method I'm using anytime I'm using a method to make it clear. So I'm going to mention here that we will prove this claim by induction on k. Okay, so suppose, I believe I called it h, yeah. Suppose hk of x is equal to negative 1 to the power of k plus 1, k minus 1 factorial, 1 plus x to the power of negative k. We're going to take the derivative of this. hk plus 1 of x is going to be negative 1 to the power of k plus 1, k minus 1 factorial, negative k, 1 plus x to the power of negative k minus 1. And this is equal to, negative signs become negative 1 to the power of k plus 2. K times k minus 1 factorial is k factorial, and that is 1 plus x to the power of negative k minus 1. And this is exactly the other side. Thus, Pn of x, so that's exactly the negative 1 to the power of k plus 1 times k plus 1 minus 1 factorial, 1 plus x to the power of negative k plus 1. That's exactly what we wanted to prove. So Pn of x becomes the sum k equals 0 to n. Well, the very first term, which is h of 0, must be done separately. So it's the sum k equals 1 to n, because the formula was different. hk of 0 divided by k factorial times x to the power of k. Now, h of 0 is natural log of 1, because it's natural log of 1 plus x, plus the sum hk of 0. If you plug in 0 in hk, which was here, you would get negative 1 to the power of k plus 1, k minus 1 factorial, 1 plus x to the power of x minus, so it's, let me write it down here. negative 1 to the power of k plus 1, negative 1 to the power, k minus 1 factorial, and then 1 plus 0 to the power of negative k over k factorial x to the power of k. So let me go back and take a look. Negative 1 to the power of k plus 1, k minus 1 factorial. Yeah, so that's what I get. This one is from 1 to n. So now after simplifying, ln of 1 is 0. So what we end up getting is the sum k equals 1 to n. Negative 1 to the power of k plus 1 stays. K minus 1 factorial and k factorial, they cancel. We are left with a k at the bottom. And 1 plus 0 to the power of negative k also disappears. So we get x to the k over k. So this is going to be the nth Taylor polynomial for 1 plus x. Okay, so that brings me to the end of this video. So next time we'll talk about, in fact, how these Taylor polynomials can or cannot approximate functions. So this would be our next discussion. Okay, so I will see you in the next video.